A very good morning, good afternoon, good evening to everybody participating in this wonderful conference. My name is Swayan Panda. I'm a postdoc fellow at the Laboratory Nacional de Astrofísica in Itajuba, Brazil, and a Kavli Boya fellow at the Peking University in Beijing. I finished my PhD last year at the Center for Theoretical Physics in Warsaw, Poland. This work I'm going to present is in collaboration with Professor Paola Marziani from INAF Padova and my PhD supervisor, Professor Bojana Cherny from CFT Warsaw. In this work, I'm going to take you on a ride of how we interpret and model the quasar spectra for super-Eddington sources. This work has been published over the last few years, and I'm going to focus on specific modeling that has been done and a work that has been submitted recently to Astrophysical Journal. So before we begin, it's a wonderful question to know what is an active galaxy. Over here on the left, I'm showing an artistic illustration where we have a black hole, supermassive black hole sitting right at the center with an accretion disk around it. Next to the accretion disk, we have broad and narrow emission line region, which are characterized by the Keplerian velocities that we see in their observed AGN spectra. In addition to these, we have the obscuring torus that allows or impedes the direct view of the central engine, and thus phenomenologically, we have the categories such as type 1, where we have a direct view, or type 2 AGN, where we do not have a direct view to the central engine very close to the black hole. In addition, we have the presence or not so efficient presence of a jet, and this additionally gives different categorization of different AGNs that we see. So that is the part with the geometry. Now, when we move on to the energetics, that is another way we study AGNs. AGNs emit on a vast scale of energies that span wide region frequencies. Most prominent among them is the accretion disk energy that is peaking in the visual to optical and UV energies, which is marked here with the red dashed line. In addition, we have the emission that is peaking in the X-rays from the hot corona, and in addition is chunked together with the soft X-ray excess. This high energy emission from the accretion disk is then reprocessed due to the presence of the obscuring torus and is re-emitted in the infrared. In addition, we have several other components such as the contribution from the host galaxy, the presence of the reflection component and the K alpha line that overall gives the broadband energy distribution AGN that we observe. A typical AGN spectra is quite useful and meaningful to study. It has primarily three components. One is the most important, the underlying AGN ionizing continuum that we can appreciate when we see the power law dependence that is embedded inside the AGN spectrum. In addition, we have certain absorption features, and more prominently for us in this talk are those emission lines, which are then categorized as broad and narrow emission lines. The broadness or narrowness of the emission line actually is related to their velocity profile that then allows us to infer their distances from the supermassive black hole. So basically, the combined information obtained from the spectra can provide us insights on the dynamics, energetics, and composition of the immediate surroundings around the supermassive black hole. Now coming on to a very specific and interesting class of AGNs, which are the narrow line Seyfert galaxy type 1. Narrow line Seyfert galaxies are thought to be the younger, less evolved versions of typical, more massive black holes. So basically, they are the sources with low mass, low luminosity, and low jet power. And eventually, they are much more interesting and atypical compared to the general population of AGNs. Certain of their salient features are as follows. The full width half maximum of H beta for these sources are below 2000 kilometers per second, and the ratio of their forbidden O3 5000 angstrom, 5007 angstrom over H beta is less than 3. In addition, one of the most prominent features for narrow-line Seyfert 1 galaxies are their strong iron emission with respect to H beta. In addition, they show stronger blue slit or asymmetries in high ionization line, such as the carbon-4 emission line. Also, narrow-line Seyfert galaxies are less common to show signatures of being very radio loud. and they are typically found to be more variable than their broad-line Seifert counterparts in the X-ray regime, although the scales of their variability in the optical and infrared is less pronounced. Here in the bottom right, I'm showing a cutout of three different kinds of spectra in the optical regime. On the top in the black, we have a typical case of a narrow-line Seifert 1 AGN. In the red, we have an intermediate type AGN, and in the blue, we have a liner type, which basically is devoid of many of the strong features of emission lines that characterize the emission from the broad emission line region. As we can see, there is the prominent bump feature around the H beta line in the left and the right regime, which is related to the Fe2 emission in the optical. As well as what we can see is the Balmer emission lines are strong, peaked, as well as broadish. In comparison, the intermediate case are much more broader in their broad emission line region, although are not as intense as compared to the narrow line Seifert. As we mentioned before, the O3 emission in the narrow line Seifert is less pronounced to their typical counterparts. So these are characteristic things in the optical. Now let's move on to have a much more broader look at what narrow line Seifert shows us in the UV regime. Here in this plot, this is a plot taken from a very recent paper by Park et al. 2022, where they show the prominence of two narrow line Seifert 1 AGNs, and most importantly, focus on the HST observation of the Markarian 493. Here in the black, we have a prototypical narrow line Seifert 1 galaxy that has been known for decades, Wiki 1. And for comparison purposes, they also show the SDSS quasar composite here. Over here, if you mark closely in the regime between 4,000 to 6,000 angstroms, we have the prominent bumps from the Fe2 emission, which is quite clearly seen in the case of Wiki 1 in the black and Markarian 493 in the red. In contrast, for the SDSS quasar composite, they are much less pronounced. As we noticed in the previous diagram before, the broadness in the Balmer lines is much more clear in the typical SDSS quasar composite, in contrast to the narrow line Seifert 1 galaxies. Now, moving on to the carbon 4 regime, which is one of the high ionization lines, we can notice that the lines are much more symmetric in the composite, while they are far more asymmetric when we go to the cases for the narrow line Seiferts. So this is one very interesting feature that distinguishes narrow line Seiferts from their typical broadline counterparts. So this is the location of the iron emission shown here, marked in the black and the red, which are much more prominent in the narrow line Seifert cases. In addition, narrow line Seifert 1 galaxies are high accreting sources, which have been shown to have shorter broadline region time lags. Here in this plot on the right, we are showing the compilation from Huang et al. 2019, where at present, about 120 reverberation map sources in the optical have been plotted to emphasize the radius luminosity diagram. In the black are the sources from their own sample of the super-Eddington accreting massive black hole project, which clearly show deviation towards shorter time lags, that mean shorter distances of the broadline region from the supermassive black hole, and thus deviate from the standard classical radius luminosity relation from Benz et al. 2013. Recent works have found that the deviation is actually related to the high Eddington ratios of these sources, which is proportional also to the strength of the iron emission that we just noticed. So by reconciling the correction for this strength of the iron emission, one can recalibrate these high Eddington sources back into the classical diagram, thus making the sources much more useful for other purposes. For example, and most prominently, for using quasars as cosmological candles. Quasars are much more interesting in the broader context of understanding the evolution of our universe, because they link the local universe to that of the early universe. Using standardizable candles, quasars, which we can understand knowing their systematics, can allow us to infer the evolution of the universe and allow us to connect the local to the early phase of the universe. So this is quite interesting and a prominent chapter that has been gaining more attention in the recent times. But before that, we need to understand what are the intrinsic systematics associated with quasars, especially the bright and accreting at higher Eddington ratio sources. In order to account for that, there is a very interesting and phenomenological diagram that is known as the quasar main sequence. This main sequence diagram is basically an analogous scheme to the Hertzsprung-Russell diagram that is used for the stars. But one interesting difference, and among many, is that quasars are more extended sources and can be categorized fundamentally by their black hole mass, Eddington ratio, black hole spin, as well as the viewing angle to the source. This makes them more challenging and more interesting in some ways to study. Here in this diagram is shown the optical eigenvector 1, which was categorized first by Borisson-Green back in 1992, where they compiled a sample of 85 Palomar-Green bright AGNs and made a PCA analysis on top of that, a principal component analysis on them. And the primary driving parameter, the eigenvector 1 that came out of that, is shown here and has been studied over and over for the last 30 years. In this plot on the y-axis, we have the full width half maximum of the broad H beta line. On the x-axis is the strength of the iron emission with respect to the H beta line, which is known by the parameter RFE2. Here we have the broad diversity of type 1 AGNs shown along the sequence. And we can clearly appreciate the sequence, and many studies have focused and found out that this sequence is mainly driven by the Eddington ratio, but not only that, it's been characterized by the properties of the broadline region themselves. And this was one of the tasks that was part of my PhD thesis, where we have emphasized and visualized an 8-dimensional parameter space in the context of eigenvector 1 sequence to understand this diversity that is interlinked with the type 1 AGNs. The parameters are basically obtained by careful and detailed analysis using cloudy radiative transfer and spectral synthesis code, which basically characterizes that this main sequence is governed primarily by Eddington ratio, black hole mass, shape of the ionizing continuum, broadline region density, the metallicity of the broadline region, the velocity distribution of the broadline region clouds, the orientation with respect to the observer, as well as the broadline region cloud sizes. Also, quite interestingly, is the detailed division of the sources as two categories called population A and population B. This is primarily done as a function of the distribution with respect to the full width half maximum of H beta. Basically, sources with velocities of full width half maximum of H beta larger than 4,000 were categorized as population B sources, while the one with the smaller than 4,000 kilometers per second were called population A sources. And narrowline CFOT1 are a subset of population A sources, which actually populate the sources below 2,000 kilometers per second and are having much more higher and stronger FE2 emission. Here I'm showing a montage, an exemplary montage that was compiled of a large set of cloudy database that was prepared in one of our past projects, where I'm showing the inclusion of the dependence of the viewing angle that was accounted in addition to the primary properties of black holes, such as the mass and the accretion rate. Here, each snapshot is basically done at a different viewing angle to the broadline region. And these montage maps shows as a distribution of BLR metallicity as a function of BLR density. And the color coding is basically the strength of the iron emission. By knowing the inclination angle from these models, we can then predict the virial radius, which can then be compared to the radius that has been accounted from the radius luminosity relation. This allows us to study not only the narrowline CFOTs, but the whole general population of AGNs, which have pronounced or not so pronounced iron emission in the broadline region. Now, we talked about the dichotomy based on the width of the full width half maximum of H beta. But there exists another dichotomy, and this time is due to the emission lines ionization potentials. The first set of lines basically includes Lyman alpha, carbon 3 semi-forbidden line, carbon 4, and such lines, which are grouped together to be known as the high ionization lines. These lines have relatively low density production and are emitted in a region which has densities less than or equal to 10 to the power 10 per centimeter cube. On the other hand, There is a second group of lines which are called the low ionization line. Primary among them are the Balmer lines, magnesium 2, iron 2 emission, and many others which have mild to higher density region where they are produced. So this is quite interesting in our line of work because we don't only want to reproduce the emission and the properties of low ionization lines, but also the high ionization lines. Coming back to narrow-line Seyfert galaxies again. Another very interesting point of narrow-line Seyfert-1 galaxies in studying them is that the shape and the luminosity of the soft and hard X-ray spectrum. And the finding that these can even accrete at higher than Eddington rate, which is why they are sometimes called super-Eddington accreting sources. One such exemplary compilation was done by Gary Ferland and his collaborators back in 2020, where they show exemplary features of broadband fitting of narrow-line Seyfert-1 galaxies and compare them to typical AGNs. Here I'm trying to mark the location of high energy bump, which is peaking in the UV up to the soft X-ray excess, especially in the case of the red curve, where we can clearly see the prominence of the big blue bump and the shifting towards the higher energies in this case, which is a typical already known narrow-line Seyfert-1 galaxy, which is accreting above the Eddington rate. So a direct consequence of such high accretion rate has been associated to the solutions of slim accretion disk. In this model, basically the structure that we normally associate the geometrically thin, optically thick accretion disk as per the standard Shakura-Sunyaev disk is no more validated. And this strongly affects the isotropic emission of ionizing photons from the disk, and thus has consequences on the shrinking of the position of the VLR that we aim to study. So to visualize this picture into further more details, this is how the situation evolves when one considers the slim accretion disk scenario. If we look zoomed in closer to the black hole, we can notice the prominence of an inner funnel, which is basically not something new, but has been analyzed and pre-analyzed in previous works. This prominence of the inner funnel really then makes the case study much stronger for anisotropic disk emission. And this then separates regions like region 1, region 2, and the broadline clouds, which are further located closer to the disk plane to receive different ionizing photon and SEDs, depending upon in which region are they located. So here I'm trying to show a schematic view of the distribution of the broad emitting line region around a slim disk scenario to further emphasize the presence of high ionization medium lines such as the carbon-4 lines here, while the characteristic broad line regions from the low ionization regime are maybe located closer to the disk plane. And this development of inner funnel actually separates them and changes the intensity of the incoming radiation depending upon where these clouds are located. Here we also show a few examples of how slim disk SEDs change as a function of accretion rate and viewing angles, in addition to change in the black hole masses. And a clear distribution can be seen, especially in the case of change in the inclination, going from the 10-degree case where they really peak up in the soft and up to soft X-ray energies, while at inclination at more 80 degrees, edge on direction actually restricts the emission range to few up to the orders of 1 Rydberg and slightly higher. Similar effects can be seen in the increase in intensity with increase in the accretion rates. So let's try to assimilate everything together by combining the information of the accretion disk SEDs from the slim disk scenario, as well as accounting for isotropic X-ray coronal emission. This is done after careful fitting with observed SEDs from Ferland et al. 2020 paper that I before showed you, especially in the cases of narrow-line Seyfert-1 galaxies. So here I'm showing a case with a typical face-on view of up to 10 degrees, about 10 degrees, and different cases from left to right basically increase in the accretion rate parameter, going from accretion rate of 100, dimensionalized accretion rate m dot 100 to 500 in the middle panel, and up to a highest case scenario of 1000. And we can clearly see the deviations and the salient features that change when one increases the accretion rate, going from 100 to 1000. Now, In the subsequent panels, I'm showing the changes that are actually happening due to the inclination change going from the 10 to the 40 degrees in the middle panel, and finally to the case of the 70 degrees, which is a much more edge-on view, where the prominence of the funnel restricts the view of the high energy photons to the low ionization BLR. So let's go finally to the results. Here we found that using this modeling approach, the iron strength increases with decreasing viewing angle. This is one of the prominent cases of the low ionization lines. And here we are trying to compare two cases, exemplary cases, theta 10 degrees versus theta 70 degrees for a m dot case of 500. What we finally figure out is that the high BLR density and high metallicity are requirements for efficient production of iron emission. These results are compatible with the observed BLR radius. Basically, the patch that we are really seeing is accounting for the observed dispersion in the radius luminosity relation, accounting for the iron emission due to the high accretion rate. So the peak values in these cases actually shift towards smaller radius RBLR with increasing viewing angles. And finally, the increased accretion rate really is accounted for higher RFE emissions. Now, complementarily, the equivalent width of H beta is also increases with decreasing viewing angle. And here as well, high BLR density is required in the case of low inclination, while the density range widens with increasing viewing angle. These results are again compatible with the observed BLR radius based from the reverberation mapping studies. And finally, to account for the high ionization case, we also study the equivalent width of the carbon-4 as a salient feature, where we find that the density range shifts toward lower values compared to the low ionization lines, which is what is also found from the studies from spectral fitting of UV emission lines. And thus, this really emphasizes that the carbon-4 emission line and similar high ionization lines are produced at a different emitting region. And they're more constrained emissions within the log n, log r space that is shown in these maps relative to the low ionization lines. So the study is really bright, and the future is very bright for us, given all the plethora of instruments that are upcoming, which will be serving as testbed to study and reaffirm the modeling approaches that have been accounted in this work. Finally, I'll leave you with my summary, and I will take questions, and thank you for your attention.